All right, let's get started. So one bit of administrative detail. This Thursday, day after tomorrow, we're not going to have a lecture. We'll have nominally a recitation, but we figured instead of having it in person, we'll just give you guys a video from last year where we had a TA explain the sort of details of how to use containers. So this is going to be useful for Lab 2. So when you guys get started on Lab 2, or I guess during lecture time tomorrow, on Thursday, you can watch this video as background material for that information if you need it. But with that out of the way, let's get started with today's lecture. So today's lecture is going to be all about privilege separation. So this turns out to be a powerful technique for dealing with bugs in our systems. So if you remember, one of the big sources of security problems in computer systems is that we have bugs, and these bugs lead to vulnerabilities in our systems. And this makes it difficult to build secure computer systems if we have bugs. So an important question is, how do we actually build secure systems despite this fact? This turns out to be tricky, and the paper we assigned for you guys to read for today's lecture is one of the interesting case studies on how to apply privilege separation to a real system. So the case study that you guys read is this paper from people that actually deployed a real system. There was a website, I guess still is, okcupid.com. It's a dating website. They have sensitive data from many users they want to keep secret, and they actually built this OKWS design and privilege separated their system in order to provide stronger security guarantees. And that's an interesting case study of how to actually push through this privilege separation plan and get something out of it. So the particular case study in the context of web applications, that's what we're going to talk about today. But in general, this idea of privilege separation is applicable in lots of domains, and we'll see many examples of this throughout the semester as we go. Make sense? All right, so what do we do about bugs in our software? There's really two plans. One is somehow prevent the bugs. And this is a fantastic plan when it works. So to the extent that we can get rid of bugs altogether, that is great. And it works pretty well, right? So if we can actually do it, it is effective at improving security when you can actually do it, when possible. So the challenge with preventing bugs in the first place, as you might imagine, is that you sort of have to know what the bug is and have a plan for preventing it. What I mean by this is that most approaches that try to avoid certain classes of bugs require you to first figure out what is a class of bugs that you should go after. So it seems relatively unlikely to be fruitful to say, oh, I just want to find any bug at all, because that doesn't really give you any sense of what exactly are you looking for, what is a bug, and how are you going to prevent it. So it's useful to find some kind of a class of bugs that you think you want to prevent. So right there, we're already limiting most of these prevention approaches to a certain category of bugs that we think we understand. So one example is buffer overflows. We really understand that's a class of bugs that's worth preventing, and we can go after that, but it's not the only class of bugs. And then, for that class of bugs, we have to have some kind of a prevention plan. So one example is the Buggy paper, Buggy bounce checking that we looked at last lecture. That's a paper that really avoids or tries to mitigate buffer overflow bugs. So for a certain class, we have a plan to deal with buffer overflows. Maybe not perfect, but get somewhere there. And this is a pretty good plan. You should probably apply it to whatever system you're designing, but it's not going to catch all the cases you might imagine, because it's going to be hard for us to enumerate all the classes of bugs and come up with 100% plans to deal with every one of those classes. Make sense? And there's many classes of bugs that you might imagine in the target application for the paper we read at. So this OKCupid website. Many kinds of bugs you could have in an application like this. So just to give you some sense of what the context is, or what their system looks like, they're imagining they have some kind of a web server running, and there's some kind of an application or some application code running inside the web server. This is the naive version of what their system might look like. And there's a lot of requests coming into this system. People might be logging in, they might be sending messages, they might be updating their profiles or viewing other people's profiles. Lots of requests coming in that have to be handled by this application. So lots of code to service those requests. And then behind the scenes, the application is probably storing data, maybe in a SQL database for dynamic user data, or maybe large things like images or photos of users, maybe get stored as files in a file system. So it's sort of a large monolithic entity that we're dealing with here in a typical web application. And there's a lot of data sort of that we might want to protect. So there's probably passwords for login. There's probably messages that users are sending to each other. There's profiles of various users. You name it, all there. Make sense? So what kinds of bugs could you imagine being in an application like this? What do we have to defend against? What are we worrying about? Yeah? SQL injection bugs. All right, so let's talk about that a little bit. So one possibility might be you sort of have some sort of a SQL query bug. So a pretty common bug indeed in web applications. What happens in one of these SQL injection so-called bugs is that an application is trying to construct a query to the database server in the back. So this is some application code you're writing, might be Python or C or PHP, whatever you have. And you're just constructing a string. So you say, select some data from some table. And maybe you say, where the ID is equal to something. And then in order to complete the SQL query, you're going to plug in the ID that the user asked for. So maybe you're selecting the profile of a friend you're trying to look up. So you might say, here's plus the friend ID. So you're constructing a giant string. This is a SQL query you're going to send to the database. And this is a fairly common buggy pattern that shows up in many, or used to show up in many SQL-based applications. This is like the buffer overflow of the database application. The problem being that the friend ID here, if this is an arbitrary string supplied by a user, or in this case maybe an attacker gets to supply a friend ID, then they could easily have a friend ID that looks like a fragment of a SQL query. So for example, the friend ID could be 5:delete from profiles. So if that is the friend ID that the adversary asks the website to look up, a buggy application might accidentally splice this friend ID into the SQL query, and then the literal string that gets sent to the database server is going to be select, profile from friends where ID is equal to 5:delete profile. And that'll maybe confuse the database server into deleting the entire profile table. This is a sort of a common mistake. The way to fix it is probably to escape the ID so that it's not an arbitrary string, and maybe you put it in quotes, and you have to escape quotes in the middle of the string, etc. But there's ways to deal with it. We'll talk about standardization later. But indeed, there's bugs quite a bit different from buffer overflows that show up in perhaps a web application. Other kinds of bugs you might worry about? I guess we could just literally have buffer overflows themselves. So, right, could be that there's some part of the code written in C. Other things you might worry about, yeah. Yeah, it's like bugs in handling security sort of decisions, access control, authorization, login. So, yeah, access control bugs. This has nothing to do with sort of a mistake of a low-level type, like a buffer overflow or splicing a string incorrectly. the application needs to decide, can you view that friend's profile or not? You got to write an if statement somewhere to do that, and maybe you just forgot. So indeed, this is like quite a different style of a bug than buffer overflows or SQL injection maybe. Yeah, other things, yeah? Yeah, potentially denial of service bugs. Maybe it's more of an effect than a bug, in the sense that maybe denial of service is sort of an outcome rather than a particular mistake that you're taking advantage of. But indeed, it's like there's maybe some mistakes that you've made in the application that make it particularly easy to run the server out of memory or resources, make it unavailable for other users. Yeah. Other bugs you might think about? Yeah? Yeah, so okay, so like similar bugs to SQL queries at the file system interface. So we had that example of the application talking to the database server, and here there's sort of SQL queries, and maybe here there's just syscall APIs accessing the file system. And one similar kind of a bug might be that you're accessing file, access bugs, and you don't properly sanitize the path. So for example, I want to load a friend's picture, so what I do is I call open on /profile / friend ID. And a very similar bug to SQL injection shows up, where the intention is that I'll open /profile / John as the file name, but if the adversary supplies a friend ID that maybe looks like .. /etc/ password, well, then the file system will open the path /profile / /etc password, which will cause maybe the operating system to open the password file and return the contents of that now. There's lots of subtle bugs to make. So the point of this is that buffer overflows are not the only game in town you have to worry about. There's lots of mistakes everywhere. And we could keep going with all kinds of examples of bugs you could make. And these are just the classes of bugs that you can broadly describe. And in any particular application, there's going to be probably even more subtle bugs that are specific to the thing you're building that matter. Make sense? Sort of the point isn't necessarily that, you have to learn about 5 kinds of bugs, even though there's lots of work on, for every one of these kinds of bugs, people have, identified it as that's an important class of bugs, and people have built tools like baggy bounce checking, effectively, to try to deal with every one of these classes. But still, it's probably not going to be enough, because none of these defenses or prevention plans are going to be 100%, and there's always more kinds of bugs that might show up. Make sense? All right, so the alternative, if we can't prevent all the bugs to begin with, is to somehow tolerate the bugs. And this is what this paper is about. And the plan is to, roughly speaking, take this giant application that we have over there that's running inside of our web server. So take this application from this diagram. And sort of the point is that many of the bugs are so damaging because everything goes into this giant application, and then the application has access to everything. It's like maximally damaging. So what we're going to do is take this application, refactor it into a bunch of little components, maybe A, B, C, whatever, however many components you have, and then we'll make them talk to each other as needed in order to make the application work. So split up the application into different pieces, and then that's going to help us deal with bugs in these different parts of the application. And there's 2 important ways in which this is actually going to help us. One benefit of splitting this up is that we're going to limit the damage. What I mean by limiting the damage is that if you break into this monolithic app, as we saw, there's a bug of any of these kinds, you can access the whole data behind the scenes. You can access all the data from the database, from the file system. If it's a buffer overflow, then anything you can do. Access control bugs, also pretty broad. And instead, if we find a bug now in one of these smaller components, the hope is that it doesn't have access to the entire database, or maybe not the file system, and so on. And that bug is not going to lead to as much problems for us if it's exploited. So that's one really cool thing. The other benefit of splitting things up is that we can actually limit maybe the attack surface as well. What I mean by limiting the attack surface is that in this big monolithic application, what's going on is that all the code is sitting right there where all the requests are coming in. So in some, at least high-level sense, if there's bugs in this application, they might be much easier to exploit because this application code is right there handling all these requests. In contrast, it might be the case that if we can split up some parts of the system into smaller components, maybe we don't need to make them directly accessible to the outside world. It might be that HTTP requests are coming into the application over here, and in the split, maybe the HTTP requests are coming here. So this guy is exposed. That's the attack surface of this. It's pretty wide to the adversary. But then all these other components are not directly accessible anymore. And maybe they're more difficult for the adversary now to exploit. Depends, of course, on exactly how you split this up, but that's at least the two things to keep in mind, two potential benefits we're going to get out of a privilege separation plan. That make sense? All right. Questions? As usual, feel free to ask questions through Kevin or the TAs if you don't want to ask directly. All right. Jump in anytime later as well. So what does it take to construct some scheme like this? Well, there's sort of two classes of challenges. One is you've got to figure out what is even the plan for splitting this up. So this is a pretty major surgery to an application. This is not something you're going to be able to do automatically. It's not like some compiler is going to take your program and split it up. This is a big decision, like architecting your software or re-architecting the software if you have an existing piece of code. And that's a real question. That's actually probably the most challenging thing in privilege separation is figuring out how are you going to restructure your application so that it actually still gets all of its stuff done that it wants to get done. The application still works, but yet it's broken up into components in some meaningful way that gives you better security. So how might you actually split this up? I guess one example that you saw in this paper is splitting it up by some kind of a service. So if your application does many different things, like you can view a profile, you can send a message, you can view a photo, those are fairly natural boundaries maybe to split. It might actually be a meaningful split, like for this case study application, works pretty well. Services or maybe types of data that it's handling, like maybe handling images is one plan, handling PDF files is a different service that you should split up, etc. So that's one way you could partition your application. Other ways that you might imagine partitioning an application. Any thoughts? Yeah. Oh, like which database is actually being accessed? Yeah, so maybe you could split up by sort of privileges or resources, yeah. Indeed, so one natural thing is like if you have 5 different tables in your database and they correspond to nice 5 pieces of code that touch that data, that seems like a great natural split then. You have sort of 5 things that are independent in your application, and maybe you want to split it up that way. Or maybe if you have code that touches the file system and then other code that talks to the database, that also might be a good split. Or in general, you can think of splitting by what privileges are going to have to give to each of these components. So as the name suggests, privilege separation involves not just splitting up the application to these pieces, but then limiting what each piece can do. So by limiting the privileges or permissions or rights that each component has, that is what's limiting the damage if that was compromised. So a natural way to think about privilege separation is to figure out, well, what are all the different resources or privileges I need in different code? Maybe that's a fruitful boundary by which I can partition. Other thoughts? Yeah?
By responsibility?
By responsibility. Yeah, so maybe by responsibility, maybe sort of that's a service kind of a thing, exactly what you mean, yeah. So I guess in some ways it depends on the application. Another way might be by user. So if your application has many users and the users are pretty separate from each other, like maybe Gmail or applications that are more user-centric and less sharing-oriented, maybe a user split makes more sense than an OKWS. Another way to think of it is, so this has been a very functional view of how to split. Another might be to focus on where you're going to be the most effective. So maybe think about splitting the Buggy code. So if there's some code that you're particularly worried about, like image codecs or video processing code or something, or some C code in your Python application, maybe you want to shove the C code elsewhere because you worry about the C code being more buggy. So that's one way to think of it, maybe Buggy code, maybe particularly privileged code like we're talking about here, maybe particularly exposed code. If the part of your application is processing raw input from the network and something else is going on, maybe it's a good idea to have the network processing part be in one place and then parse the requests and then send it off elsewhere. So maybe by exposure or attack surface is another way to think of it if you're going after sort of limiting the attack surface kind of a benefit. Make sense? So this is super application specific, and these techniques are sort of why I think this paper is pretty exciting. So OKWS really does an interesting case study trying to sort of struggle with this question. We have this application, it's a real system, somehow we got to split it up and they actually work out. Okay, well, here's an example plan that actually works for this real system, and it's not just a toy study, they really run it, so they must have gotten everything. It actually does work. So this is the part where OKWS is really informative as sort of an example of how to make this work. The other challenge in making privilege separation work out is sort of a more mechanical question of how do you actually make the isolation work? So much of the mechanics, so we need to break up an application into these boxes. Once we've decided here's the code that goes into box A, B, and C, we got to somehow isolate them from each other. So we need some kind of an isolation plan, of course. And this paper uses Unix user IDs and CH roots and other machinery. Then we need to actually figure out, once we've isolated them, we need to allow them to actually share. So there's some plan for allowing controlled sharing, like the arrows I have in this diagram. If we need some component to talk to a different component, we got to realize this somehow. So there's got to be some machinery to make that happen. And the other challenge, of course, with all this isolation and sharing abstractions is that it comes often with a performance overhead. So a challenge is to make all this work well while still getting good performance. So both sides are challenges. This is more an application-specific challenge. This is where the case study, I think, is pretty informative. This is a more mechanical and a sort of common challenge in a sense that the answers to these questions are probably going to be the same for many applications. This is where OKWS is a bit of a dated paper. You've probably noticed that it doesn't look like how you would build a modern system at all. You probably wouldn't build a web server in C++, especially not application code written in C++. You probably wouldn't use Unix user IDs. There's maybe better mechanisms around these days. So I think that part of the paper is kind of interesting to look at, but maybe not as interesting as the particular split that they chose and how they architected the design. We're actually going to talk next week about various answers to these questions and how Amazon, for example, does isolation. And they have a much more, perhaps, principled and stronger isolation plan, and they worry a lot about performance. So we'll look at the isolation machinery in more detail next week, but in this lecture, we'll try to focus a little bit more on understanding the split and what benefits we can get with various architectures. Make sense? Any questions? Yeah.
Not a technical question. I'm just wondering why they chose to do a dating website of like all applications.
So the dating website came first, not OKWS. So this guy founded this company, OkCupid.com, way before, actually before I think he became a PhD. He was a PhD student here at MIT in our research group. And he had the startup from quite a while ago, so he started the company. And they were having trouble writing secure code because the problem was that he was a relatively expert programmer. He could write good code, but he needed to hire lots of people to build lots of applications that would match people differently on his site, to build surveys, all kinds of fun features that are more feature-centric and not security-centric. But when they hired people that were not security experts, they're like dating experts perhaps, they didn't write secure code, especially given the thing was written in C or C++ at the time. You know, recipe for disaster, as you can now see. So they actually had some security problems before they deployed OKWS. And this was very much a solution to a real problem these guys had. So it wasn't the case that they sort of said, here's a research paper, we want to write this, let's do a case study of building a dating website. It was really much more the other way around. The guy started this company, had a reasonably successful dating website. It got more successful after OKWS, probably not because of OKWS, but and then when sort of he was in grad school, he decided, that was interesting, let's write a paper describing what we happen to have done. Yeah. Other questions? Hopefully we'll get this guy to actually give us a guest lecture on a different topic. He actually founded another company later called Keybase, which got acquired by Zoom. So this guy, Max Krohn, is now in charge of developing end-to-end encryption for Zoom. So hopefully he'll give a guest lecture on Zoom end-to-end encryption maybe in a couple of months in this class. That's sort of a very much on this tangent on why this paper and who. All right. So let's look at this case study of OKWS and try to understand how are these guys splitting their service. So what's going on in their architecture? So just to remind you, the original picture for them looked very much like this picture right here. And this probably looks still like many web applications you would build today. Like if you build some Node.js application or a Python Flask website, it probably looks like this picture. And to some extent also suffers from these bugs. Maybe you don't have buffer overflows for the most part if you write in Node.js. Or maybe you do if you call out to some C image processing library. But nonetheless, that's sort of the starting point for them. And where they ended up is a very different design where the first order separation for them was really splitting up by service, as we were talking about here. So in their design, they really had sort of service 1, service 2, service 3. These are the main components running in isolation of each other. And these services might be things like, as we were talking about, like a photo viewer or photo sharing application, maybe profile matching, maybe some kind of a messaging system. But one thing to keep in mind is that because this was a dating website, this sort of influenced the kind of data sharing patterns that are going on. So it's not like Gmail where every user is looking at his own bunch of data. Instead, all the users are mostly sharing data. So many of these services look at data of other users, trying to find matches for you. Maybe you look at photos of other users. Maybe you process their profile information, etc. But it's very sharing oriented, which influenced to a large degree, I think, the choice of going with this service-based separation. Because at the end of the day, these services, or most things that you would do in this website, involve touching data of many users, not just yourself, but maybe in a limited way, as we'll talk about, scoped by service. All right. So these services need to actually store some data, and at the back end, for practical purposes, they still run a SQL database. So some kind of a SQL database engine is still there, but there's this component that they call the database proxy that sits in front of the database server, between the database and the services, that is going to interpose on these requests. So instead of having the services talk to the database directly, there's this database proxy, and the services have to talk to the database proxy first in order to access any data stored at the database. Make sense? All right. And driving all of this, like where the requests come in, there's a service they call OKD for the OK dispatcher. And this guy is where the HTTP requests come in. So if you have some HTTP request coming into this website, it goes and gets handled by OKD. That accepts the TCP connection, handles your HTTP request. And then once it decides which service should get this request, it's actually going to route this connection to the appropriate service. And the service can actually handle whatever it is the request is asking for, access the database, send the response, etc. Make sense? Questions? All right. And then there's sort of two more sort of orchestration pieces. One is that there's a logging service on the side. So they wanted to keep a log that was going to be protected even if there's a compromise in the system. So they set up a separate OKLogD component that collected the log messages from all these services. So all the services log into OKLogD, and I guess OKD probably logs into there as well for anything that needs to be logged. And then there's a launching daemon, the OK launch daemon, OKLD, whose job is to start this whole thing on a machine. So you have a computer, you boot it up, the first thing you run is OKLD, and this guy is going to start OKD, it's going to start this service, going to start this service, and so on. And I guess also starts the logger. Everything gets started by this launcher. Make sense? Questions about this design? Yeah? I think this is a reasonable, I guess, one view of the architecture of this design, yeah, in terms of, what we're looking at. So these are sort of the logical components that they have running on their different machines. There's a bit of a split that I'm not showing, which is that they have multiple machines in their sort of server room or data center, if you will. I should say, right, this is the early 2000s, so there was no AWS. You wouldn't run things on AWS directly. What they had was like a rack in some co-located facility in some data center where Max would go and plug in machines by hand and plug in wires and wire things up. And what this looked like is there's probably a couple of computers, maybe 2 or 3, that were front-end machines. So this is some kind of a front-end server. And the front ends run everything except the database and the database proxy. And the reason for that is that except for the database and the proxy, all these components are mostly stateless. So there's no user data stored here durably. And if a request arrives on one of these guys and then this machine reboots and another request arrives, that's fine. The database is still there. We'll get to the database. So that's the reason why they might have multiple front-end servers. And then there was one database server machine that was running the database and the DB proxy. And there was lots of connections from here to this database server. And physically, there's actually sort of a connection to the internet here. So you actually plug into some switch from your ISP into these servers. And then this was actually a private network behind the scenes. This was a common practice back in the day because this was not sort of a shared cloud provider that you run everything on. So it actually seemed to make sense to have like a private switch here and then plug all these machines into your private switch. So that's the physical topology underlying this logical view. Make sense? So a number of you guys asked actually, well, the Google paper made a big deal about like, oh, no network isolation. We shouldn't rely on any kind of network level security mechanisms. I think it's partly because Google is operating in an assumption that you're going to have lots of shared workloads all sharing the data center, and it's not practical to have custom one-off setups. But these guys really had like one application. There was nothing else running on these machines. So for them, this was an okay setup. The database server is just not reachable from the internet. It's just on a private switch behind the scenes. Question?
With regards to user data, the single database makes sure they have the same key in all these methods. But what about the configuration file? Is there like a network file?
So you're pointing out, there's some state, a little bit, there's some config file for how to launch these front ends. So you're right, the database server is where the main state is, and in particular, the way to think of it is the database server is where the really mutable state is, like the users updating their profile, etc. There's something that has to deploy these config files, like for the launcher, onto all the front-end servers. I imagine that initially, this was just done by hand. Max would SSH into these machines and put the same config file onto all the machines. And maybe they used some automation deployment scripts, but actually wasn't even that prevalent at the time to sort of automate the deployment of machines nearly to the extent that you would find it today. Sense? Other questions? All right. So that's sort of the component separation. So why is this split good for them? So why are they so worried about bugs in the service code? So I think I sort of mentioned this a little bit, is that their goal was really to make it possible to iterate much quickly on their actually features that are facing the user. So they wanted to be able to have lots of developers write service code. So this is sort of, fast development time, if you will, and maybe by non-security experts. And that's sort of the thinking why they're not going nuts trying to necessarily separate every component up into little pieces. They're really looking, to some extent, not just by service type, as we were talking about before, but in some sense, they have some intuition about where the bugs are going to be. And in particular for them, it's the services. That's what they're thinking is going to be written by not super expert developers that might make mistakes. So that's why they're really focusing on separating out these services. And the thing that's going to make this fly, in some sense, is the DB proxy that's going to limit what each service can do. So this guy is going to get the requests. And the database proxy is going to look at the requests coming from various services and decide that, this is not allowed request from this particular service. And that's really where the damage limits come from, so to say. And as a result, if a compromised service is broken into, then at least you don't have all the data being leaked. Maybe some data, of course, all the data that was accessible to that service might get disclosed, but it's not a full database dump, perhaps. So one maybe important corollary is that if some experimental matching service gets compromised, then maybe at least the user passwords or the session data or cookies don't get disclosed on the internet, because that's not accessible to this experimental profile matching service. Make sense? This is sort of the line of thinking that I think gets these guys excited that indeed it's going to save them from compromised services. So one thing I wanted to look at, or one way to understand to what extent their design actually defends against various compromises, is to look at the different components that these guys have constructed in their design and try to understand, on one hand, what are the privileges that the component has, which goes hand in hand with how much damage can the component do if it gets broken into. And on the other hand, what is the exposure? How likely is it for the bad guy to break into that component? So we really want to make sure that the things that are super exposed maybe don't have a lot of damage, and vice versa. The things that have a lot of damage, if they go wrong, somehow they're not super exposed in our design. Make sense? So let's try to step through the design of OKWS and all their components and try to understand what is the sort of damage from compromises. So the thing we want to talk about is, let's look at various components. Let's look at what the privileges are, or what the damage would be if this thing was compromised. And then let's look at the attack surface. How would the attacker have to mount an attack, or what are the bad inputs they could provide to try to break in? Make sense? All right. So let's start somewhere. I guess, what's the most privileged component in this whole design? What's the most damaging part if someone broke into it? Yeah? Yeah. The database proxy is indeed somewhat trusted indeed. So let's talk about that. So if the database proxy gets compromised, the damage, I guess, is potentially pretty big, right? Like, all the database data. So everything that's in your database could be leaked out. I guess maybe one thing that the paper talks about that I didn't draw in this figure is they imagine that they could have multiple database proxies. So they're thinking that if I have multiple databases for whatever reason, I'll probably stick a separate database proxy in front of each of them. But nonetheless, this is still a fairly substantial amount of damage if this thing were compromised. So what's the attack surface? How would a bad guy try to break into the DB proxy? Or where would an attack have to come from? Yeah? Yeah, so I guess how would they, like, okay, so I suppose, yeah, like you could physically break into the data center and plug in. That's probably not quite what they're worried about. So in terms of software, I guess what would have to happen? Yeah, so probably have to be that, service gets compromised and service sends a request to the DB proxy. And probably it's a little bit stronger than this even because the DB proxy is presumably implemented in a way that very quickly rejects requests or connections from services that are not authorized to talk to it. There's this token thing that we'll talk about in a second. So probably the most interesting kinds of attacks would be from services that are actually authorized to talk to this DB proxy. So one nice thing going on here, right, is that there's quite a bit of damage this guy could do if it's broken into, but might actually be reasonably tricky to break into it because you have to first break into some service to send requests to this guy, and then the particular attack surface is these requests that are actually formatted using this RPC library that they implemented. And one reason to mention this is that this RPC library brings at least some plan for how do you consistently parse input messages. So it's not like they have a handwritten parser that could be totally full of bugs in this DB proxy. Probably it's like a reasonably carefully written, consistent library that takes messages in and maybe doesn't have as many or hopefully any memory allocation bugs and so on. So that's the attack surface for this DB proxy. Other components that are privileged here in this design. Yeah? The launcher, yeah. So that's actually pretty privileged, right? So actually, if we look at how it actually runs, we haven't talked so much about the isolation machinery details, but this OKLD component actually runs as root, which gives it full privileges, full administrative access to the machine on which it runs. So it doesn't give it direct access to the database server, but it means it can take over anything on the machine on which it runs. So OKLD can probably peek into the config file, all the services. It can get all the database access tokens that the services use. So if OKLD is compromised, it can steal all the data from the services, including the tokens. It can go talk to the DB proxy, get all the data that the services have access to. So in many ways, it's also pretty bad. So, all service state, which might actually mean that also means all DB state, to the extent that the DB proxies are going to give it out based on the tokens of various services. So it seems pretty damaging, actually. How would you break into OKLD? Can you send it requests? What inputs does it take at all? Yeah? So you're saying can't really send it anything. Does it listen to anything? Okay, actually, I guess once it starts, does it accept any inputs at all, or does it just exit? Yeah? So you're saying when you restart the computer or something? Okay, so yeah, so I guess that's a good point. So to some extent, one thing we're not discussing at all is like what's outside the model, which is useful to think about. So probably like Max Krohn could SSH into all these machines, and that's one attack vector that sort of undermines this whole design. So you're right, and maybe like more engineers at OkCupid would be able to do this. So that's a good point, and probably OKLD might be restartable or whatever, configurable through SSH. So that's probably actually much bigger than any attack vector that OKLD directly exposes. But indeed, as you were pointing out, OKLD has almost no input. So basically the only input it ever accepts from the network, so to say, aside from the out-of-band SSH stuff, is it waits for the processes to crash. And if a process crashes, it gets this 1-bit signal effectively saying process X crashed, it restarts it. That's a very small interface, so it seems pretty unlikely that there would be a bug in how it handles getting this one signal saying a process crashed and you restart it in order to be able to exploit it. So almost none in terms of the attack surface of OKLD directly. Make sense? Yeah? So okay. So one thing you're asking is, okay, so OKLD sort of creates these children by forking, and there's various bugs you could have in how you fork. So for example, you might leave some of your own file descriptors left over, or some of your memory left over. I think the focus here is, or their sort of assumption is that Max writes OKLD and other things, and he is very careful. And in particular, the goal is not so much to focus on bugs in OKLD, although, okay, good to think about them. But I think they're assuming OKLD is well written, and really sort of the services are the more buggy part, but you're exactly right. Like, OKLD is a trusted component in a sense that maybe one way to think of this attack surface is that there's sort of two different kinds of security problems you might have. One is that you just do something stupid by yourself, like you run, and you leak data. You didn't even have to, that hacker didn't even have to try to break in. So that would be a relatively easier bug to find because you don't have to think of a clever attack. You can just run it and see, is it leaking something? Maybe a little bit more subtle than this, of course, but the difference is that in one case, you can examine the state and see, did something bad happen? In another case, now, in this attack surface, what we're talking about is there some subtle way the attacker could supply some input that I didn't think of? That's a much trickier kind of a bug to find. But, yeah, good point. Like, we gotta make sure that this thing is, to some extent, correctly implemented. Yeah. All right. Make sense? These two parts? All right. So let's talk about maybe, I guess there's the service itself. That was our whole plan. So what if there's a bug in the service? What's the damage? Yeah? Okay, limited to what service can access. Yeah, so probably it's whatever the DB proxy allows for that service. So if you compromise the photos service, the DB proxy probably lets you look at the photos of all the users, but not the passwords and maybe not the profile info and things like this. What's the attack surface? If you want to break into a service, how do you do it? Where would you start? Yeah? Yeah, so HTTP requests are certainly one way. Anything else? I guess the other thing that it actually consumes is the data coming from the database. So if you can somehow maybe plant some bad data or, specially crafted data into the database, maybe through the same service or maybe through a different service even, then the service that you're trying to compromise will read it out of the database and process it. So maybe there's sort of data in the database that you could inject. So you have to be careful with processing data from the database as well. Probably not a great idea to trust that all the data in the database has been properly sanitized. Okay, so that's the attack surface. And this is sort of the main story we were talking about already, that not going to be disastrous. Probably does leak something, but not the end of the world. Make sense? Okay, so let's maybe finish up and talk about the other components here that there are in OKWS. So what haven't we covered? I guess there's the OK dispatcher, OKD. How bad it is if this thing is compromised? Anyone else? So if you break into OKD, what could you do? Yeah? Okay, so one thing you're proposing is that if you break into OKD, I can send requests to all the services. So that's true, although this might not really expand the power of the attacker because I was already able to send arbitrary HTTP requests to the system. So I could have probably already asked a well-meaning OKD to send me a request to any service. Maybe I could control more of the request, but probably that's similar. Yeah? Intercepting requests, yeah, so that might be more damaging indeed. So it might be that once you compromise OKD, it's a long-running process. So you compromise it, but it keeps running. And in particular, it keeps seeing more HTTP requests come in. And one thing you could do is probably monitor what the users are doing. You can monitor the requests. You can monitor the responses. one damaging thing you might be able to do is actually like steal the cookies of the users. So if I see a user request come in with a particular cookie, you could take it and then send your own requests in impersonating that user. So I guess the damage in some sense is full HTTP requests of existing users, and perhaps the cookie in each of those requests is maybe the most damaging part, is that you'll be able to steal everyone's active sessions. Yeah? Yeah, so that's another good point, I guess, is that, yeah, if you break into this thing, you could make the whole machine stop serving requests. So that's a good point. I guess we actually haven't talked about this to some extent in these other components. So, yeah, so if you break into a service, the nice thing is that at least you don't DOS the whole site. You just DOS the photo sharing service, not messaging or login, perhaps. For the launcher, I mean, it's hard to compromise maybe, but if you do compromise it, I guess you could make it stop restarting. Although, having root is probably damaging enough already there. You could just reboot the machine at that point. And for DB proxy, you could also, of course, steal the DB data, but also, I guess, stop any database accesses, which is going to halt the site. So maybe the only positive DOS story here is that services maybe are somewhat DOS resilient. All right, so what's the exposure of OKD? Where are the bugs going to be there? Yeah, perhaps. So that's a good point. Okay, so you're saying, if any of the services rely on OKD doing some filtering, then maybe it's back to this attack that you described earlier, where being able to send arbitrary requests to a service now becomes more interesting. That maybe some service was expecting to not even receive requests. Like maybe it's the photo sharing app or service. It wasn't expecting to get requests for the messaging app. Maybe it does something not quite right if it gets such a request. So, okay, indeed, could be that you might be able to exploit a bit more of an attack surface of these services by controlling OKD. Fair enough, yeah. All right, so what's that attack surface? What does it do with potentially attacker-controlled data that it might be exploitable? So this thing is pretty minimal. So all it actually does is really just parses one line of HTTP requests. Actually just parses the first line of the HTTP request and actually sends the rest to the service to parse further. So fairly minimal amount of work being done on OKD, so this maybe gives you some hope that it's not super likely to have a bunch of bugs that you could exploit, even though it's widely available or accessible to the attacker. All right, and the last part of the service is the logger, OKLogD. So how bad is it if you break into the logger? Is it going to be damaging? Yeah? Yeah, okay, so one possibility is you might delete logs. I suppose another possibility is maybe you can view logs, depending on that sort of question of what exactly you're logging. Maybe there's something sensitive there, maybe not. But, not the end of the world, probably. Deleting logs maybe is unpleasant, but if that's the only thing that happened, not horrible. So what's the attacker? Question, yeah. Yeah, so actually, maybe the way to think of it is not just delete logs, but actually like totally modify logs. Append stuff to the logs, edit logs. Yeah, so that seems a little unfortunate, yeah. So could fill up the disk with garbage log entries, etc. Some of the stuff isn't specific to compromising OKLogD. So for example, if you compromise a service, you could probably already send garbage to OKLogD and so on. But at least in that case, if you compromise a service, maybe OKLogD will say, oh, this is all garbage from that service. And then you could figure out where it came from. Whereas if you compromise OKLogD directly, well, now you're stuck. You can't even tell what the heck happened. You can't trust any log entries at all. Yeah, that's a good point. Yeah. All right. So what's the attack surface for this stuff, for OKLogD? How would you break into it? You'd probably have to break into some existing component first because it's not listening on the network directly. So really sort of break into some service or OKD or something else. And then from there, you'd be able to maybe send log entries that are funny in some way. Yeah, so that seems like the most likely attack surface for OK log D. Make sense? All right. So this is one way to try to understand whether some kind of a privileged separation plan is good or not, is to really think critically, which we've done to some extent here, about how exposed are different parts of your system design, and how bad is it if they get broken into, and hopefully the most likely things that get broken into that are most exposed to random network inputs are hopefully not super sensitive. And to some extent, maybe this is true here. I mean, for these services, these are the ones that are dealing the full HTTP request complexity, and they're, somewhat limited by the DB proxy, so that was the goal all along. And other components seem actually pretty good too. Make sense? Questions about this stuff? All right. So let's try to figure out what are the limits of this design. So I guess one question you might ask is, so if you were given a design like OKWS, where would you try to attack? What do you think is the most vulnerable place? I guess we talked a little bit about out-of-bound attacks like bribe max or like steal as a SH key. That's probably at least worth trying. But I guess within the scope of the design, what do you think are the still most juicy targets? Yeah? So you're saying, okay, still the services, right? So, yeah, so probably that's the case. So, still the services. And that's probably true, right? So they probably are the most buggy part here because they sort of, the whole plan was to let not so security conscious programmers write this code. And we did limit the damage somewhat, but doesn't mean that they're any less buggy. So probably you would be pretty effective at finding a bug in some service and then getting a dump of at least that view of the database. So maybe there's a bug in the photo sharing app. You could break into there, get a list of all the photos in the system. Maybe you don't get the passwords, but that's probably at least a somewhat successful attack if you were after some data out of this site. Make sense? Anything else? What might be useful? Yeah. The DB proxy, you're saying? Yeah, so that might be a pretty good plan, in particular, if you were to compromise a service, right? So the DB proxy, the reason you would go after it is that, it does have access to a lot of DB state. It's a little bit sheltered by these services, so you'd have to first find a bug in a service after, compromising a service. But nonetheless, you could maybe chain these things. First, compromise the service. Maybe these guys aren't super bulletproof. And then you could start seeing, now that I can actually talk to the DB proxy directly, are there any bugs there? So yes, that's probably a pretty fruitful way to go. Any other things? So one part we sort of took for granted so far is maybe the OS kernel that underlies this whole picture. So it's indeed needed to implement this separation. So you rely on Linux to keep all these services and processes apart from each other. And the kernel probably isn't super exposed directly to the network. So if you weren't running code on this machine yet, you might not be able to break into the kernel with quite as big of an attack surface. But after you compromise the service, again, you might try to find some bug in the OS kernel. Again, after some kind of a service bug. This kernel, at least the way they implement separation between, or isolation between their components, they do rely on the kernel. And the Linux kernel is a pretty big piece of code. It's like millions of lines of code. And bugs are found in this thing probably every couple of months for sure, where you can get root access by taking advantage of some bug in this kernel code. So in some ways, their plan for how to actually keep these things isolated from each other isn't that great. So next week, as I mentioned, we'll talk about better ways to isolate things from each other using VMs and containers. Yeah, maybe looking for bugs in the kernel is not a bad idea once you can get code running on the machine, probably by breaking into some service. Make sense? Other things? Or is that sort of the main attack avenues you would try against the system? These are probably the sort of main parts, I imagine. Maybe you could try OKD, the dispatcher that does this HTTP parsing. It's kind of limited in parsing just one line of HTTP, so maybe relatively unlikely to be a bug there, but nonetheless, it's exposed and could probably give you a lot of damage if you were able to break into it. Make sense? All right. So let's look at a couple of other aspects of this design. One thing that is sort of quite important to this whole OKWS plan is this idea of a database proxy. So let's try to look in more detail at how this works and how they made this fly. So one thing to ask, I guess, is like why... Okay, so we have the SQL database somewhere on the database server, and then we have these services running in front of it, service 1, service 2, service 3. Why do these guys really need a database proxy at all? Could they just let the services connect directly to the database? What would have to happen in order to connect directly? Probably, okay, so one thing, of course, we need is for different services talking to the database, we need to somehow interpose on what data they're actually able to access. And most database servers come with some kind of a plan for limiting SQL queries, or not limiting SQL queries, limiting what kind of data you can access. But one maybe problem these guys are concerned about is that these database servers are gigantic pieces of code themselves. So they're, I think, partly worried that if they were to allow a service to talk directly to the database server, even if the database server had some notion of access control internally, there's just a lot of code in the database server that could be buggy or have buffer overflows in its own right. Like the database server parsing a SQL query could have a buffer overflow. That would be really bad. So I think this is partly why they think the DB proxy is a good idea for them, because it really allows them to sort of have much tighter control over the SQL queries that are being sent to the backend. So it's not that the service can execute arbitrary SQL queries, but it's only the SQL queries that the DB proxy has whitelisted. So the way this probably works is that I imagine the DB proxy config file, there's something that says, service 1, it can run queries 1 and query 2 and so on. And service 2 can run query 5 and query 6. And maybe a couple more. And these are the only SQL queries that you can run with some parameters plugged in. So very restrictive compared to using some kind of access control engine inside the DB server. So I think they're getting probably some mileage out of just sanitizing or tightly controlling the kinds of queries that you can even issue at all to the backend database here. Make sense? Probably a good idea. Or like typically, applications don't worry about this too much because they have a world like this. So if you have an application that's issuing garbage queries to the database, you probably have the application compromised and has full access to the database anyway. But in their case, they actually sort of imagine a world where a service is compromised and the database has to stand up to arbitrary garbage queries. And they're thinking, the database proxy is going to be a better job of filtering this out than letting the DB server try to deal with this. Make sense? All right. And they use these tokens that I guess the homework question was about, basically in order to let the DB proxy figure out what service is talking to it. So as we were talking about in the physical layout diagram on the board on the way over right, this is all running on the front-end machine. And then this part of the diagram is running on the back-end server, on the database server. So this is a TCP connection. And the DB proxy doesn't really know who is connecting to it. So the token is really a way of identifying which service is trying to connect to the DB proxy. So probably it says, in the config file for the DB proxy, it says, token 1 is this, and token 2 is this other service. And then in the OKWS config file, probably the administrator, when they write down the config file, they put down the tokens for each service. So they say, give token 1 to service 1, and give token 2 to service 2. And when they start, they can connect to the DB proxy and authenticate themselves. So this is also, I think, along the lines of what we were asking in the homework question, or in the reading question, like what's the damage from getting a database token? And probably it's, first you have to get access to this backend network somehow, maybe to compromise that service or any other service of your choice. But once you have access to the DB proxy, then you can impersonate that service, and it's as if you compromise that guy. Make sense? So to some extent, this diagram also explains why the DB proxy goes with the DB server instead of having the DB proxy run on the front-end machine. The DB proxy is stateless, but they really want this DB proxy tightly coupled to the database backend so the database is not exposed over the network to arbitrary inputs. So they really want to sort of have the network stop here and don't have the database listening on the network at all. Make sense? Question? Where, sorry? Yeah. So I think what's going on is that on each front-end machine, there's a config file for the OKLD daemon. And in that config file, they define all the services. They say, run service 1 with this binary, with these arguments. And I imagine one of the arguments is just the token in the config file. Or maybe it's like a special field because they know every one of these guys is going to need a token or something like this. But the config file, I imagine when they list out all the services that have to be run, like right there in a text config file, they have the token supplied for each service. So I imagine it's up to the administrator to manually sort of configure the DB proxy saying, here's a token I just generated randomly. It's going to go for service 1. Here's the queries it can do. And then they copy paste this token into the config file. I sort of imagine that's probably the workflow they had in mind. Make sense? All right. So the last sort of topic I wanted to discuss about their design is their choice of separating by service. So they make a bit of a deal about this in the paper where they discuss all kinds of, could we separate by user instead, etc. So let's try to understand, would user-level separation have been fruitful for them, or maybe where would it have worked or not? So service versus user privilege separation. So are there examples where service separation is about the best you can get? What I mean by this is, are there maybe services for which user separation wouldn't give you anything stronger in terms of security benefits? So one example I'm thinking maybe is, maybe a profile matching service. So this is a service whose job is to sort of scan through all the profiles in the database and find profiles that maybe are close to you in terms of what you want to what friends you want to find in this site. So that service fundamentally needs to have access to all the data of all the users that are needed by this service. So there, user separation wouldn't really win you anything. So it's really no difference between what you would get if you had user-level separation or purely service-level separation. So they're not really losing out by much here. I think this is one of the reasons why they're thinking service level is pretty good for them. Are there services for which user-level separation could have gotten them more security? So maybe something like maybe messaging, sending messages could be a case where you could win. So maybe if you had per user isolation of messaging, then compromising one user's messaging service would mean that only that user's messages are broken into. So if the adversary finds a bug in their, or exploits a bug in their copy of that service, they'd get their own messages, but not anyone else's messages. So this could be a difference, so it might be a big difference, depending on how you structure it. So there's some opportunity. They could have done better with a more clever separation plan. What about login? So they probably have a login service as well. Would the login service been more secure if they had per user separation? Yeah. Yeah, so that's a good point. So the login service, you might think that, it's all per user, but in fact, you can't even figure out which instance, which user it is to begin with. So all the login requests are indistinguishable until they've logged in. So in some sense, you must route them to the same service. It doesn't really matter, or you can't figure out which user it is. So maybe the only thing you could have done is every login service goes to a freshly started copy of the login process. Then you would have made sure that any prior exploits are cleared out because you restarted it. But per user or not, that's not really the thing. So maybe it's like, fresh process. That would have made a difference. But per user isn't really going to help us here, indeed, because we don't have the user yet. Make sense? Any questions about this? All right. So one thing you might try to figure out is, what else could we do in OKWS to maybe get some of this difference for things like messaging? Could we do something better for isolating services that have a little bit of a per user flavor to them, like only getting the messages that are sent to you as opposed to getting everyone's messages? So one thing that might be interesting to look at is sort of a spectrum of isolation. So we looked at, so OKWS has this model of having a process per service. And of course, the data that you can get is all the service data. And the extreme point that they discuss in the paper, and they say it's too expensive, is have a process per user. So this thing is really expensive because the server doesn't have enough memory to maintain a running process for every user of the system. There's millions of these users. And they're thinking, it's too expensive to launch a process every time a user request comes in, because that would really increase the cost of handling each HTTP request. They're actually pretty excited that they're able to handle these HTTP requests so cheaply in OKWS. So could we do something in the middle? So one question is, if you guys think back to the Google architecture paper, you might remember that in the Google design, they had processes per service, effectively. They had a VM running for every service in the Google design. But they still had this ticket thing where services had to have user permission tickets that granted them access to the data of a specific user. So what does this look like in OKWS land, if you will? Any thoughts? Yeah? Yeah, so maybe you're hinting, we'd need a fancier DB proxy of some kind. So I think you're right. So probably what it would look like is that we'd probably still have a process per service, because that's the thing that's really expensive. We can't have a process per user. But instead of allowing this process per service here in sort of this is the full OKWS, in this model, you can access all service data. And that sort of makes sense. But here in this intermediate design we're hypothesizing about, inspired by the Google design, we're thinking, maybe there's a process per service, but only you can access the data of the currently logged in users. So the overhead isn't really there from running many processes, very much like in the Google design. But maybe we could limit it so that when you break into a service, you can't steal all the data. You can only steal the data of the users that are currently logged in or currently issuing requests. So it's potentially a stronger version of what OKWS does, because suppose that there was some rarely used service, like an experimental, matching service that very few users used. It's kind of why it was buggy, because no one bothered to use it and didn't find the bugs. So then, if there was a bug there that the attacker exploits, you can only steal the data of the users that have used that service. But it could be kind of cool. Or same for like a messaging. If there was like a bug in some video chat application they had and relatively few people bothered with the video chat app, well, it would only leak the video chat data of those users. Does this make sense? Any questions? So let's try to sketch out what it would take to extend OKWS to support this sort of Google-like user ticket model. So I guess the components we'd have to worry about are probably, well, let's look at the life of a request. So we have HTTP requests coming in. I'm just duplicating some part of that diagram. We're going to hit OKD. OKD is going to route our request to some kind of a service. Then that service is going to go to the DB proxy. And then this DB proxy is finally going to relay our request to the database server in the back end. So if you want to add this notion of only allowing access to the data of the currently logged in users, so remember we have this table in the database proxy where we're talking about the service can issue query 1, query 2, etc. So what would have to change to implement this new finer grain separation design? Any thoughts? Yeah? Okay, so you're saying, okay, so here we have to somehow figure out which user is getting the request. So somehow we need to parse the request and identify the user. So that probably means that we're going to have to actually parse in OKD, not just the first line, but probably the whole HTTP header has to get parsed. So we'll probably have to look at the cookie and use the cookie to figure out which user it is. So OKD probably has to be a little bit more sophisticated now in order to figure out which user is making a request, not just which service it's going to. And then we probably actually wouldn't want to send the cookie to the service. That actually would be a slight improvement in security in some ways. But instead, what we do is we actually first, before handing off the request to the service, we probably have this new arrow that would be used by OKD to tell the DB proxy that, service 1 is now running on behalf of some user. User X. So this is the kind of message that OKD would have to send to the DB proxy, and the DB proxy would probably maintain some kind of a table of users that have recently invoked this service, and then these queries would probably be parameterized by the user on whose behalf you're making this query. So if this was a service for fetching messages, then this would be a query into which you have to plug in a user ID. And part of the RPC from the service to the DB proxy would be, I want to run query 1 with user X. And the DB proxy will only do this if it got this message from OKD recently. Make sense? Question?
So why does OKD contrast to
Yeah, so I think you could imagine, okay, so your question is like, why do we have this arrow instead of having it go to the service and the service talk to the DB proxy? I think you could imagine maybe both ways working. I think you could maybe give the cookie directly to the service, and then the service could just give the cookie to the DB proxy. Then the DB proxy would have to figure out what to do with the cookie. So maybe this is a way to centralize the cookie processing. Another benefit is that this cookie doesn't happen to show up in this buggy code. So if this is compromised, you don't get the user's cookie. But you're right, there's many ways to do this. In fact, the Google design does it in a different way altogether. They don't fully describe it, but they have some fancy crypto going on of like signing some message. But this is sort of, one fairly simple design you could imagine. Make sense? All right, so this is kind of like maybe a concrete example to help you guys appreciate what that Google paper was talking about, and also maybe some flavor of what it means to wrangle with one of these privilege separated designs and how to add new features to it, or maybe strengthen the isolation. So as far as I know, OKWS didn't do this. Probably wasn't super important to them. But it was, I think, still used actually OkCupid now, 15 years later or so. Not used by anyone else as far as I know, but it's a cool case study, and I think to some extent influenced, I think, people building privilege separated services in general. All right, so that's it for this case study. See you guys next week. We'll talk about isolation machinery. No lecture on Thursday. Sorry? Oh, the recitation is going to be online. There's like a video you can just watch online. So no physical recitation. But yeah, watch the video whenever you feel like learning something for Lab 2.